Hello everyone, I am Nanjun Swami GS, Assistant Professor, Department of Chemistry, JSS Academy of Technical Education, Noida, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. This lecture I am going to discuss about infrared spectroscopic, means some of the topic which are included in infrared spectroscopy. This is lecture number 2. In the lecture number 1, I have already discussed the introduction of infrared spectroscopy, means what is infrared spectroscopy, what is the principle and theory, and what are the infrared region, and molecular vibration, fundamental vibration, and selection rule for infrared spectroscopy. After that, I am going to discuss this video. In this video, I am going to discuss how the molecular, means how the frequency it will vary, means how the frequency will vary with respect to the molecular vibration. Before that, we already known infrared spectroscopy is one of the useful, means widely used technique to determine the function group and to identify the molecular interaction in a sample. We can easily determine it by using this infrared spectroscopy. Means the infrared spectroscopy is mainly based on the principle of molecular vibration is due to absorption of infrared radiation. By absorbing infrared radiation of an organic compound, the molecular vibration will take place. Means the absorption, due to that absorption of infrared radiation, it will give infrared spectrum. Based on that, means using that infrared spectrum, will get what is the function group which are present in the sample. Means in the infrared spectrum, we will get vibrational frequency. Means if the molecule is having permanent dipole moment while vibrating, that molecule is called infrared active molecule. Infrared active molecule will absorb infrared radiation and it will give infrared spectrum. Using that infrared spectrum, we'll get vibrational frequency of the respective functional group. But we can also calculate the vibrational frequency by using theoretical method. This video lecture I am going to discuss about theoretical calculation of vibrational frequency and how the vibrational frequency it will vary by its chemical nature of the organic compound. Let us discuss. First, if we consider a diatomic molecule contains M1 and M2 molecular mass, M1 and M2, if this figure 1 represents figure 1, this figure represents M1 diatomic molecules having M1 and M2 molecular mass. In the diatomic molecules, if the mass of both the atoms are equal, means there is no change in dipole moment will occur, as the molecule is infrared inactive. If the two atoms is having different atomic mass, means change in dipole moment will occur, means the diatomic molecule is infrared active. According to that Hooke's law, means the classical vibrational frequency of diatomic molecule, it has been derived from Hooke's law. Hooke's law means Hooke's equation is using to calculate the vibrational frequency, of diatomic molecule of in infrared spectroscopy. Means we can able to calculate theoretically the vibrational frequency of diatomic molecule. In that Hooke's law, Hooke's law represents mu is equal to 1 divided by 2 pi root of k divided by mu. Mu represents vibrational frequency. Mu represents frequency. 1 divided by pi, 1 divided by 2 pi, pi value we already known, 3.14. K is nothing but with force constant. K is nothing but force constant, means the force constant is nothing but the strength of the bond divided by mu. Mu is nothing but reduced mass, means the reduced mass mu is equal to formula m1 into m2 divided by m1 plus m2, reduced mass. If we substitute the reduced mass value, we will get 1 by 2 pi c into root of k into m1 plus m2 divided by m1 and m2, equation 1. If we are measuring the infrared spectrum by measuring infrared spectrum in terms of wave number, means the wave number relation mu is equal to mu bar is equal to mu divided by c, means 1 by 2 pi root of k into c, means 1 divided by 2 pi c root of k into m1 plus m2 divided by m1 into m2. We already known c value. C is equal to speed of light 3 into 10 to the power of 10 meter per second square, meter per second square. This expression, this equation is using to calculate the vibrational frequency of the diatomic molecule. Means how the reduced mass is related with the vibrational frequency, how the force constant is related with the vibrational frequency. We can easily get it by this equation. Means if the force constant k is increases, means if the force constant is more, means high, the vibrational frequency is also more. If the reduced mass is high, the vibrational frequency is less, means it is vice versa. Means the reduced mass, if the mass of the atom, if the molecular mass increases, means if the molecular mass is inversely proportional to vibrational frequency, the force constant is directly proportional to vibrational frequency. We'll take one example. First, the calculation of vibrational frequency. We can calculate the vibrational frequency of bond with a reasonable accuracy in the same way as we can calculate the vibrational frequency of a ball and spring system. The equation of calculation is Hooke's law, is mu is equal to 1 by 2 pi. We know that one. For example, take one example. We can calculate the approximate frequency of CH stretching vibration from the following data. The given data is K is equal to 500 Newton per meter, 500 5 into 10 to the power of 5 grams per second square into m, means 1 Newton per meter is equal to 1 kg into meter per second square, means 1 Newton is equal to 1000 grams per centimeter. Okay, mass of carbon is 20 into 10 to the power of 24 grams. Mass of hydrogen is 1.6 into 10 to the power of 24 gram. We can calculate the frequency of this molecule CH stretching vibration. Mu is equal to 1 divided by 2 pi, means 22 divided by 7 value. Substitute the value given data to the equation. We will get 9.3 into 10 to the power of 13 per second of vibrational frequency. In order to express the vibrational frequency into wave number using this relationship, mu bar is equal to mu divided by c. Mu we already calculated, the value is 9.3 to the power of 13 per second divided by c, speed of light 3 into 10 to the power of 8 meter per second, where c is the velocity of the light, means speed of the light. We'll get the wave number is equal to 3.1 into 10 to the power of 5 meter per meter. Means we are expressing the wave number in centimeter. That's why 3100 per centimeter is the value vibrational stretching frequency of CH. Here we can observe the vibrational frequency of bond is expected to increase when the bond length increases and also when the reduced mass of the system decreases. As an example, stretching frequency of C double bond C, stretching frequency of C double bond C, C double bond C is greater than C single bond C, means the bond strength between C double bond C is more when compared to C single bond C. That's why the stretching vibration of C double bond C is greater than that C single bond C. The second example, stretching frequency of CH is greater than C single bond C, means the force constant is same but the molecular mass, but the reduced mass of C single bond C is more. That's why the vibrational frequency of C single bond C is very less when compared to CH bond. Means CH bond stretching frequency we already calculated 3100. The reduced mass is less in CH molecule. The same thing, next stretching frequency of CO carbonyl group is greater than that C single bond O, means the force constant of CO is more in carbonyl group, in CO is less, means force constant K is less, the strength of the bond is less, means strength of the bond is very poor, strength of the bond is poor. That's why the vibration frequency is less. Next example, if we compare to the vibration frequency of OH and CO, OH is higher vibration frequency, vibration wave number when compared to CO, because OH molecular means reduced mass is 17, the CO reduced mass is 28. So that OH, it will show higher vibrational frequency. Next, force constant. We know the force constant K for the single bond is 5 into 10 to the power of 5. Double bond, for double bond 10 into 10 to the power of 5. Triple bond 15 into 10 to the power of 5 dynes per centimeter. Remember, higher wave number is equal to higher frequency, means higher frequency is nothing but higher wave number. The vibrational frequency of bond will increase when the strength of the bond increases, is also already discussed. The same thing when the reduced mass is decreased, means the reduced mass is inversely proportional to the vibrational frequency. For example, will discuss increase in the bond strength from in single bond to double bond to triple bond. The same, some of the example we are discussing some of the example. First, CN bond, carbonitrile group. C, when the given data is K, the given data is K value, force constant value, force constant 5 into 10 to the power of 5, mass of carbon 12, mass of nitrogen 14, 12 divided by 6.02 into 10 to the power of 23, 14 divided by 6.02 into 10 to the power of 23, because 12 is AMU. We are going to convert the actual atomic mass of the element, means we are divided by with Avogadro number. Okay, next speed of light is 3 into 10 to the power of 10 centimeter per second. Substitute the value to calculate the vibrational frequency or wave number by using Hooke's law equation. Mu is equal to 1 by 2 pi c root of k into m1 plus m2 divided by m1 in m2. Substitute the given data, substitute the given value to the equation. We will get the wave number 1145, means 1145 centimeter inverse wave number. Next, the same molecule but the bond strength is same, means the single bond to double bond. The force constant is 10 into 10 to the power of minus 10 into 10 to the power of 5. Same, the molecular mass is same, but the strength of the bond is more, K value is more. Correct? Substitute the value to that Hooke's law equation. We got 1619 centimeter, means 1619 centimeter. Okay. Next, when we increase the bond between Cn means single bond to double bond, the vibrational frequency 1145 to 1145, it increases to 1690. Yes, na? Okay. Next, if we increase the bond between Cn, C triple bond N, force constant value 15 into 10 to the power of 5 dynes per centimeter, mass of carbon, mass of nitrogen is same, speed of light is 3 into 10 to the power of 10. By substituting the given data value to Hooke's law equation, we'll get the value 1983 centimeter. We can compare, means while increasing the number of bonds between carbon and nitrogen, the vibrational frequency is increased. Means we can observe from the figure 2, here figure 2, this figure comparison of wavelength, stretching frequency and wave number of bonds with different bond strength. Here this Cn the wave number means the distance between two consecutive crest or trough, lambda is more for Cn. The lambda is less, the distance between consecutive crest and trough is very less in C triple bond N. The lambda value, distance between two consecutive crest is very less, lambda value is less, means the low lambda value means higher frequency and higher wave number. High lambda value means the first figure, C single bonds in high lambda value means low frequency, lower wave number. Means when the increase in the strength of the bond, it will increase the stretching frequency and wave number. Next example, decrease in reducer mass mu. Decrease in reducer mass means you compare CS bond, carbon and sulfur bond. The K value, the force constant value single bond is 5 into 10 to the power of 5 dynes per centimeter. Mass of carbon, mass of sulfur, we know 12 and 32 are molecular atomic mass divided by Avogadro number, and speed of light. Substitute the value to the Hooke's law equation. Hooke's law equation will get the vibrational frequency mu bar value is 985 centimeter. Here the strength of the bond K value is same for two molecules, CS bond as well as CH bond. K value is same, but the reduced mass is different. This M1 M2 value is different. So that the vibrational frequency is also different, means wave number is also different. Means when the reduced mass is less, the vibrational frequency is more, wave number is more. When the reduced mass is more, vibrational frequency is less. Next, we'll compare these two. CH bond, CH diatomic molecule is having less reducer mass, so that the lambda, the distance between two consecutive crest or trough is very less, means lambda is low, lambda means higher frequency, means higher value. We already known that one, the relation between frequency with lambda means frequency mu is equal to 1 divided by lambda. Clear? Good. Next, C single bond S, higher frequency means lower frequency, lower wave number with higher lambda value. Means means the distance between two consecutive crests is more higher lambda value, lower frequency. Means when this comparison of wavelength, stretching frequency and wave number of bond with different with reduced mass. Next, we'll discuss some of the vibrational frequency of some functional group and some of that stretching and bending vibration. First, OH group, OH function group. The stretching vibration, it will 2600 to 3600, 3600. The NH stretching group, it will come from 2300 to 3500. C double bond C stretching frequency is around 3000. The aromatic hydrogen, C double bond CH stretching vibration, aromatic hydrogen vibration, and C triple bond CH stretching vibration, it is coming around 3000 wave number. CH stretching vibration is coming around 2900. CHO stretching vibration, it is coming around 2600, 700 to 2800. Carbon dioxide CHCO stretching vibration is coming around 2500 to 3000. And C triple bond C stretching vibration 2000, around 2000. And CO stretching vibration is coming around 1500 to 1700. Amide bond NH bending vibration is coming around 1600 to 1500 to 1700. C double bond C isolated, it is coming around 1600. C double bond C aryl conjugated is coming around 1600. Means on the C double bond C, it is coming around, the wave number is 1600. But in the fingerprint region, means halides is CL or CF or CI or CF, CL, CI. This is fingerprint region. CO ether group, it is coming around 1000 to 1300. This is some of that vibrational, means wave number of some of the functional group. Next, what is the application of this IR spectroscopy? Finally, IR spectroscopy has primarily been used for the structural elucidation and have been used for identification of unknown organic sample and to determine, means to identify the purity of the sample in organic synthesis. And the IR spectroscopy have been applied to investigation of proteins, peptides, and hydrogen bond in dynamics and the hydrogen bonding polymer blends. Okay, we can easily determine the molecular interaction of the sample. Finally, the IR spectroscopy is being utilized as stem cell studies, material science, catalysis, and reaction kinetics. Means to determine the reactant kinetics, means to determine the rate of the reaction. This IR spectroscopy is also one of the useful technique. Thank you. If there is any query, please contact this mail ID.